Electric energy is indispensable for maintaining the IoT society, as well as the human activities. To realize the decarbonized society, power generation using clean energy sources such as solar, hydro, and wind power is attracting attention. Energy Materials Science Divisions of Tsukuba Research Center for Materials Science, TREMS. University of Tsukuba promotes research and development focusing on small environmental energy sources that are not yet utilized. Our division aims to drive the sensor modules that support the IoT society by the environmental small energy source. Such technology is called as energy harvesting. In the IoT society, where whole the things are connected to the internet, a huge number of sensor modules are used. In order to maintain the IoT society, it is necessary to replace a huge number of batteries. A fundamental solution for the battery problem is energy harvesting. Energy harvesting devices continue to provide power without battery replacement. Temperature change and heat flow are typical examples of small environmental energies. Such energies can be converted into electrical energy by utilizing the electrochemical reaction of materials. The Energy Materials Science Division is exploring and developing material systems that enable more efficient energy harvesting at lower cost. We proposed tertiary battery that converts a small temperature change into electric power. Tertiary battery is a battery with a 0-volt voltage. When the battery is heated under open circuit condition, a cell voltage is generated proportional to the difference in the temperature coefficients of the redox potentials between positive and negative electrodes. When the battery is connected to an external circuit, current will flow until the cell voltage becomes 0. When the battery is cooled, a cell voltage is generated. When the battery is connected to an external circuit, current will flow until the cell voltage becomes 0. Thus, the tertiary battery produces electrical energy in a thermal cycle between heating and cooling. The performance indicators of a tertiary battery are the thermal voltage and discharge capacity. At present, our tertiary battery produces 40 millivolts voltage by a temperature change of 30 degrees Celsius. The tertiary battery is expected to derive a semiconductor device with use of a boost circuit. We have succeeded in describing the thermal voltage and discharge capacity by the electrode parameters. We are developing high-performance materials based on these relations. On the other hand, liquid thermoelectric conversion device, LTE, has long been known as a technology to convert temperature differences into electric power. The LTE has a very simple and inexpensive structure, consisting of 2 electrodes sandwiched by an electrolyte solution containing a redox pair. A heat flow in the LTE makes the hot and cold electrodes. On the cold electrode, reduction reaction proceeds and electrons flow out. On the hot electrode, oxidization reaction proceeds and electrons flow in. The parameters that governs the conversion efficiency of LTE are the electrochemical Seebeck coefficient, electrical conductivity, and thermal conductivity of the solution. We recently discovered that the electrochemical Seebeck coefficient of iron ions becomes much higher in organic solvents. Furthermore, the thermal conductivity is much lower in organic solvents. In other words, LTE using organic solvents can convert a small heat flow into a huge thermal voltage. The heat flow generated from a human body is about 100 watts per square meter. An LTE using acetone solution will produce 15 millivolt voltage from the heat flow. Energy and Materials Science Division is conducting research and development on energy harvesting to construct the IoT society.